Welcome to this PowerPoint on the average value of a function. So I just want to go through the notes since I was absent on Friday and go through some of those example problems on that classwork section of the average value packet that you should have received in class on Friday. We'll go through that first page, the first few questions, and that should give you enough examples to try the homework problems that I had originally assigned for this weekend prior to me realizing I wasn't going to be in school. So I want to start a little bit with the pictures that are on the top of that packet, and I want to really show you a visual idea of what we're about to do with the algebra and the calculus. So if you look at that series of 4 graphs that are in the packet, okay, now mine are shaded because yours are copies, so if you want to shade them the way they are on this PowerPoint, that might not be a bad idea for you to see. The copier didn't see that, I guess. So if you look at that first integral, okay, or this first picture that we have here, let me get my pen. Let's assume that that integral from 0 to 2 is 2. Okay? This area under the region from 0 to 2, this shaded region here, has area 2. The question that we want to ask ourselves is there a rectangle that has base 2? So from 0 to 2, this is the base of the rectangle. Can we draw a rectangle using a height from one of the points between 0 and 2 that forms a rectangle whose area is equal to the integral from 0 to 2, which in this case has area 2. Okay, so let's look at this first one. We started at 0, and we went across, and we see that this rectangle, whose height is f of 0 and whose base is 2, is clearly not equal to the definite integral. We said, well, how about we go over to x equals 2? And make that the height of the rectangle. And we draw this picture. So we've got still base 2, height f of 2. Now clearly that is way too big to have the same area as the definite integral from 0 to 2. In fact, it covers the entire region from 0 to 2 under the curve and all this junk above. So that has to be a much bigger rectangle than what we want. Somewhere in the middle, though, at this value c, if you notice, you draw out this rectangle from f of c across from 0 to 2. If you take the little piece that's above the curve here and fill it in here, it's going to end up being roughly, well, exactly the same area. So this rectangle here that we've drawn at C gives us a very close, if not exact, representation of the integral from 0 to 2. And in fact, that idea of fitting your curve into a rectangle is the mean value theorem for integrals. And here it is. If f is continuous on a closed interval from a to b, there must be a c in that interval such that the integral from a to b of f of x dx equals, and this is a very strange bit of notation to see, but we'll explain it, f of c times b minus a. So basically what that means is, if you think of this side as the formation of the rectangle. The area of a rectangle is length times width, or base times height. In the case of this notation, the height is at f of c, and the base is b minus a. It's the two endpoints of your limits of integration. So in other words, the area under the curve between a and b of f of x can also be expressed as the area of a rectangle whose base is b minus a, and whose height is some point c comma f of c. Okay? Now, one other thing that's related to the mean value theorem, and it's going to come up in the problems, is the idea of an average value of a function. This f of c that is right here in our equation for the mean value theorem, that is the average value of a function from a to b. So in other words, if we take the integral from a to b of f of x dx and divide it by the difference in the two limits, we get our average value, which is f of c. And notice, all I did was I took my mean value theorem statement and I divided through by b minus a, and now I get this blue equation here. Okay, and that's going to help us determine the average value. It's the height of that rectangle that's going to form the entire area of the definite integral. Okay, we'd like like to look at some examples from the classwork section of the packet. We could actually apply this theorem and some of these formulas to some functions. So question number 1 asks, given the function f of x equals x squared plus 1 on the interval from 0 to 2, find the average value of f of x. So we'll use our formula for the average value. We're basically considering the two endpoints a and b to be 0 and 2. That's our function. So we want to basically do the integral from 0 to 2 of f of x dx, but now we want to divide that by the difference in the endpoints, 2 minus 0. So what I usually do when I do these problems is I'm going to pull out, and actually an alternative way of writing the formula is 1 over b minus a times the integral. I think it's just visually more appealing to pull that out, but it doesn't matter either way. They'll accept it written either way. So we're doing 1/2 the integral from 0 to 2 of x squared plus 1 dx. So this is just a regular old definite integral problem with the added step of multiplying our final answer by 1/2. So let's do that integral first. Okay, so we take the antiderivative of x squared, becomes x cubed plus 3. The antiderivative of 1 becomes x, and we'll evaluate that both at 2 and 0 from our fundamental theorem of calculus. So at 2, the antiderivative is going to be 8 over 3 plus 2. And then at 0, the antiderivative is going to be 0, so I really don't have to factor that in at all to the problem, because we're just going to subtract 0 from all this stuff. So we'll add the 8/3 and the 2, and we get 14 over 3, which now becomes 7 over 3, because 14 goes into 2 7 times. So that right there is our average value. That's the height of a certain rectangle whose base is 2. That gives us an area that's equivalent to the integral from 0 to 2. That's visually what's going on. So now if they ask you, well, what C is generated by the mean value theorem or guaranteed by the mean value theorem, all they're saying is, okay, so 7/3 is f of C, right? If you take this equation, you move the b minus a over. Remember, f of c is on the other side. So all we're saying is, where on the curve does x equal 7/3, or does the function equal 7/3? So 7/3 equals c squared plus 1. And now we can solve that equation for c. So we'll bring the 1 over. We get 4/3 equals c squared. We square root both sides, so plus or minus 2 over root 3 equals c. But remember, we're only dealing with the interval from 0 to 2. So the negative part, we can just get rid of and just treat this as 2 over root 3, which is the same as 2 root 3 over 3 if you rationalize your denominator. Okay, so there's one example. Of course, it wouldn't be a lesson without a trig example. So let's do sine x from 0 to pi. Same procedures. Let's get the average value, and then let's figure out what c between 0 and pi guarantees that we're going to get a rectangle equal to the definite integral from 0 to pi. All right, so for starters, we want to set up our average value. So we know that that average value is going to equal the integral from 0 to pi of sine x dx divided by pi minus 0. So we can say 1 over pi times the integral from 0 to pi sine x dx, which equals 1 over pi. Okay, well, we got to take the antiderivative of sine. Be careful with this. This is why you have to have these studied. We want the function whose derivative is positive sine. If you say cosine, that's wrong, because the derivative of cosine is negative sine. So that must mean the antiderivative of positive sine is negative cosine x, evaluated at pi, and then again at 0. So we get 1 over pi. We take the negative cosine of pi. Well, cosine of pi is negative 1, so the negative of that is positive 1. Cosine of 0 is 1, so the negative of that is going to be minus 1. So we do 1 minus negative 1. The definite integral from 0 to pi of sine is 2, but we multiply that by 1 over pi. So 2 over pi is going to be the average value. Okay? Now, the next step is to basically figure out, well, what value of c is going to get us that? So if 2 over pi is our f of c, we just basically have to solve the equation sine c equals 2 over pi. All right, this would probably be something you would need to use your calculator for, because I don't think many people can do the inverse of 2 over pi, but that's what we would do. C is going to be arc sine of 2 over pi, so we can undo the sine function on the left. And I went to my calculator earlier, and as a decimal in radian mode, I get 0.690 as my C value, and that is definitely between 0 and 3.14, so we're good for that. All right, so that basically means if you go to your sine wave and you go from 0 to pi, which is right here, if you go over somewhere to 0.6, the rectangle you formed from 0 to pi at the base and 2 over pi is the height, this rectangle is equivalent to the area under 1/2 of the period. That's the graphical representation of the algebra we just did. Okay, I don't want you to lose sight of both of those. They're both equally important representations of these types of problems. Okay, let's move on and let's just look at one more. This should be enough to get you going for the homework. Okay, here's one that basically takes what we were just looking at with particle motion and throws in an average velocity. I could very well see, I know when I gave you that free response question last week, an old one, this wasn't one of the subparts, but I could also see, and I have seen other old AP questions, where average value is one of the subparts. So it's kind of important to see this in the context of particle motion. So we're told that there's a particle that moves along the x-axis, and its velocity function is the natural log of t over t, where t is time. We want to know what is the average velocity of that particle from 1 to e. Okay, so let's set up our average velocity formula. So we're saying that the average velocity is going to be the integral from 1 to e of the natural log of t divided by t dt all over the difference in the endpoints, so e minus 1. Okay, we'll pull that e minus 1 out and just worry about the integral, because this integral is a little bit, not nasty, but a little more involved than the last couple, because we have a natural log and we have a t. So if we think about that, and we stare at it a couple seconds, we look, hey, this is a great candidate for u substitution, because I have a function in here, natural log of t, whose derivative is also part of the integrand, 1 over t. So maybe we make u the natural log of t. That would make du 1 over t dt. And then if you want to change your limits of integration, well, at the upper limit e, when t equals e, we see that u is going to be the natural log of e, which is 1. And when t equals 1, u is the natural log of 1, which is 0. So this becomes 1 over e minus 1. Now in terms of u, the lower limit is 0, the upper limit is 1. And we get, it's just going to be u du. So the integration has just been much easier. Notice I did not change my limits of integration for the average, because the average is all about doing things in terms of t. So we would not change this, and we would get a much different answer if we changed this denominator using our u values. Okay, so keep that in terms of t if you ever do use a u substitution. Treat it as like an independent part of the problem. So our antiderivative will be u squared over 2. We're evaluating that from 1 to 0. So we get 1 over e minus 1 times 1/2, which will be 1 over 2 times the quantity e minus 1, or 2e minus 2, however you want to say it. So it's a weird number, but it's a number, and that is the average velocity of our particle from 1 to e, given the fact that that is its velocity function. Okay? Hopefully this has given you enough examples to try the homework assignment. And remember, the homework assignment is on the homework page, problems 1 to 2. It's actually 10 of them, because they're broken up into subparts with letters. Like the directions say, do not use calculators for the entire first question, and parts A and B of the second question. You're allowed to use the calculator for C and D, because in order to solve those equations to do the mean value theorem, you're not going to be able to do it by hand. You're going to need to use some calculator magic. All right. If you have any questions about this stuff, please email me over the weekend. We will talk about it more on Monday a little bit, but I know we have a shortened schedule because of Mass. So best of luck on the problems, and I'm looking forward to seeing everybody back to school on Monday.